Hello everybody, I'm Édouard Bonnet and I will be talking about the inapproximability of the diameter problem. And instead of starting with diameter, I want to start with some background on conditional lower bounds. So there are a variety of assumptions that you can use to derive lower bounds for problems in P, and surprisingly one of them concerns the complexity of a problem which is NP hard. It's the SETH, or strong exponential time hypothesis. So it says that basically solving SAT cannot be done faster than brute forcing over all possible assignments of variables. So this is the precise statement. And it comes from a paper where ETH was the star of the show, so SETH was just defined in the conclusion. But here we will be more interested in SETH. So ETH, for your curiosity, is that 3 SAT cannot be solved in sub-exponential time. So you have this chain of implications. So SETH is stronger than ETH, which is in turn stronger than P different from NP. So those assumptions are currently commonly used to show lower bounds for NP hard problems. But in 2005, it was first used to get a conditional lower bound for a problem in P. We will see this because it will be very relevant to the diameter problem. So this was done for a problem called orthogonal vectors. And then from 2014 up until now, there are many such lower bounds for a problem in P that are conditional upon the SETH. So okay, it might seem strange to reduce from SAT to a problem in P. Let's check if it makes sense, and we'll check on precisely the problem that we will care about here. 2 orthogonal vectors. So you're given a set of 0, 1 vectors, and you want to decide if 2 are orthogonal. So if the dot product of 2 of them is 0. So if you start from your n variable instance, phi, you can say build your construction, your instance of 2 orthogonal vector in exponential time, because we just want to eventually contradict the SETH, so get something better than 2 to the n. So you have some like 1.99 to the n if you want time to build your instance. And let's say you manage to build an instance of 2 orthogonal vectors where you would have 2 to the n over 2, where n is the number of variables, vectors. So what? And okay, it's a reduction, so the yes instances are mapped to yes instances and no instances to no instances. So what would that imply? Well, if you have such a reduction, you're basically saying that if you can solve 2 orthogonal vectors in subquadratic time, in this time here, then, well, you can use this reduction to refute the SETH, because you need this time to build the reduction, the construction, and then big N, the number of vectors, to the 1.99 that would correspond to this here, which is also 2 minus epsilon to the n. So this refutes the SETH. Okay, so it sort of makes sense. Let's see actually the reduction in some details. It's a very nice reduction by Williams. So you what you do is that you take your variables and you split them into 2 balanced parts. So we'll have the red variables, the blue variables. And okay, the red correspond to the set A, the blue to the set B. Then we build the vectors in the following way. So we have some indices, so those corresponds to the indices indices, for our vectors. So the first two is just for you to pick something corresponding to red, something corresponding to blue. And the important part is the other indices from C1 to C8. So what are C1 to C8? Those are the clauses of the set instance. And we'll put a 1 for the vector corresponding to A1. So what is A1, I should say? A1 is a partial assignment of the red variables. So we'll have 2 to the n over 2 such AIs, and same for the BIs. So if I put a 1 here for vector A1 at index C1, I'm saying that A1 does not satisfy C1, and I will put a 0 when A1 satisfies a clause. So I get like this some vector for, well, that correspond to partial assignment A1, and I do the same for all the partial assignments. So you see that to find two vectors that are orthogonal, you need to find two vectors where you have at least one 0 at every position. So it forces you to take one red vector, so to speak, and one blue vector. And then, well, because of our encoding of putting a 0 when the clause is satisfied, orthogonal vectors will exactly correspond to satisfying assignment. So you have a partial assignment of the first half of the variables, partial assignment of the second half of the variables. So this corresponds to a total assignment, and it needs to satisfy all the clauses. So that's a very nice idea, and you can generalize it to a reduction from set to k orthogonal vectors. So let's maybe wrap up what we saw here. So from this instance with n variables, m clauses, we built 2 to the n over 2 plus 1 vectors. The number of coordinates were number of clauses, basically, plus 2. And you even have that 2 to the small of d times subquadratic in the number of vectors would break the SCTH. Actually, we'll be more interested in this consequence, that is, you cannot get something subquadratic, even if the dimension, even if the number of coordinates is logarithmic, because you see that m here, well, is polynomial in the number of variables. You can make it polynomial in the number of variables, so it's logarithmic in n. So you can actually make it a constant times log n, but here we won't really care about it, so I just put this log to some constant to the n. It's good enough, and as I said, there is the same lower bound. I mean, you can do the same trick, splitting in k part instead of 2, and you get this lower bound for k orthogonal vectors. So it's about time to define the diameter problem. So in this problem we are given a graph, and we want to compute the largest distance between a pair of vertices of this graph. So fixing a pair UV, we're looking at the distance between U and V, the length of the shortest path between U and V. And yeah, we want to compute the largest such number. So we'll be dealing with graphs potentially with edge weights and with edge orientations. So if we have edge weights, the length of the path is naturally the sum of the edge weights along this path. And if we have edge orientations, we can take the arc only in one direction. And now this order u comma v is important, so we'll consider all the ordered pairs uv. It's very much possible that the diameter is realized by per uv, so the distance from u to v is large, while there could be just a gnaw back from v to u, so the distance from v to u could be just 1. Okay, so in weighted graphs, we don't know how to do anything better than solve all pairs shortest path, and that would take cubic time. But if we don't have edge weights, then there is we can solve the problem in roughly matrix multiplication time. And if you're unweighted and sparse, so if your number of edges is roughly the number of vertices, then you can build a shortest path tree from every vertex, and then in quadratic time you get your diameter. You can 3/2 approximate the most general version, so with directions and edge weights in this time, m number of edges to the 1.5. If you scale this down to sparse graphs, it gives you this algorithm that is in contrast with this lower bound that we will see on the next slide. That if you want to get just slightly better than this quadratic algorithm here, well, you cannot get slightly better than this ratio 3/2. So under the SETH, there is no 3/2 minus something positive approximation in subquadratic time. And this uses the lower bound that we saw for two orthogonal vectors. So this is a reduction by Roditi and Vasilevska-Williams. It's again a nice reduction. It works like this. So you make two copies of your vectors. Here you have one vertex per vector, and you also have one vertex per index. And you add two vertices, one universal to the first copy and the indices, and the other universal to the second copy and the indices, and you link them by an edge. So up to this point, you can check that all the pairs that are not of the form a vertex here and a vertex there in B, all the other pairs are a distance at most 2. So now you introduce the interesting edges, and you do it in the following way. So you add an edge between a vector and an index if the vector at this position has value 1. So you do the same for copy A and copy B. And now if you take a pair of vertices in A and B that are not orthogonal, then it means that there is an index that they share and they have a 1. So it corresponds to a path of length 2 in our graph. So they are at distance 2. So if all of them are non-orthogonal, if the two orthogonal vectors is a no instance, then it shows that the diameter is 2. While if you have two vectors that are orthogonal, now you cannot find an index where both have an edge towards it, so the shortest path is 3. So the distance is now 3. So it shows that it's difficult to distinguish from diameter 2 to diameter 3. And that concludes it, because you see that the number of vertices is linear basically in the number of vectors. So a better way to represent the results for diameter than this list that I had 2 slides ago is to show them in this 2-dimensional space with runtime in 1 dimension and the approximation factor in the other. So this, for instance, would correspond to an exact algorithm in quadratic time. This is, as we said, running n BFS from all the vertices. And if you run just one BFS by the triangular inequality, you can show that it's a 2 approximation. So you get those 2 points, and in between this result that we mentioned, the 3/2 approximation in time n to the 3/2. So this lower bound we just saw, and this lower bound is that you cannot do better than 5/3 approximation if you want running time better than n to the 3 over 2. So it was originally shown by Backers et al. But then Lee showed it in the most simplest variant of diameter, so with that is the undirected, unweighted diameter. And our contribution is to add this new red point here that says that you cannot do better than 7 over 4 approximation in time better than n to the 4 over 3. So this is a restatement of our result. And the way we show that is, our plan is to show hardness of deciding between diameter 4 and diameter 7. So this gives this approximation factor hardness here, 7 over 4. From now an instance of 4 orthogonal vectors. So maybe let's take some time to say what 4 orthogonal vectors is. So the generalization of this orthogonal vectors thing is that you want to find here 4 vectors such that at each index among those vectors you find one with a 0 and this precise index. So for these 4 orthogonal vectors, we can afford to have a cubic blow up at most. So we want to build a graph now with n to the 3 vertices and O tilde of n to the 3 arcs, where big N is the number of vectors, and that would account for the running time, which is not available to us, otherwise it would break eventually the SCTH. So this is not a surprising starting point. So the reduction that we saw was 2 orthogonal vectors and 2 versus 3 diameter, and the result of Lee that we won't see is 3 versus 5 diameter hardness and start from 3 orthogonal vectors. Okay, so let's jump into our construction. So we have 6 sets of vertices. We'll specify later how they are built, and also we'll specify the edge relations between those sets, but there will be edges only where you see a red edge, only between 2 sets linked by a red edge. So our intent is that if there is if the 4 orthogonal vectors is a yes instance, we want that there is a part of this quadruple in ABC, part of this quadruple in DCB, that are distance 7 from the element of ABC to the element of DCB, and that otherwise, if we are dealing with a no instance, then all the pairs of this graph considered in both directions are at distance at most 4. And we add the vertices U and V and the weighted arcs that you see here. So for instance, there is an arc between U and the set AB. It means that we link U to all the vertices of AB with this relation of an arc starting from U and of weight 0. So when you see no arrows, it means that it's an edge or a double arc. And we do this so that some pairs of sets are at distance at most 4, no matter what the instance of orthogonal vectors is. So it's the case, for instance, with a pair of the form ABC ADX or ABC AB. For instance, here I find from ABC to AB, I have a path of length 4 no matter what. So the pairs that are undecided, and there should be such pairs because we want, in the case of a yes instance, a large distance between ABC and DCB, are the following. So from ABC to ADY DC DCB, from AB to DC DCB, and from ADY to DCB. After the paper was put on archive, Daly, Ruford, and Wien showed a much simpler and nicer way to try to do what I was doing, is to actually put those 6 arcs, and you actually don't need weights. So maybe let's not focus too much on this part. So if you do this, you need to also clickify ADX, but you can do this. It doesn't really pose any problem. Okay, so now let's see how we define those sets and the edge sets between them. So we'll see the set of vectors as 4 copies, A, B, C, D, so that when I write tuples of vectors, you can tell by the name from which set it comes. But all those things are actually copies of S, and the dimension is L. So A, B, C, and DCB are just triples of vectors. In AB, and this will be the same in DC, we have 2 vectors and then 3 indices. And the first vector should be 1 on those 3 indices. And the second vector should be 1 on at least 2 of those indices. So similarly with DC. In ADY, we have similar tuples, but now both A and D should take value 1 at ijk, and in ADX almost the same, except now of those 6 values at least 5 should be 1. So now for the edges, so let's describe the regular edges, so the edges that you see in black. So between ABC and AB, and same between DCB and DC, we have edges of this type, ABC to ABijk, where you don't change the 2 first vectors. And this edge exists if there is an index among ijk where both C and B takes value 1. The other regular edges, so between AB, ADX, DC, and ADY, the rule is the same. You don't change the indices, and you change one of the 2 vectors. Index switching edges, they just change the indices and keep the vectors the same. They exist in AB and in DC, they are in blue. And finally, skew edges, they do the same, but they go from ADX to ADY. If there is no orthogonal quadruple in S, I claim that all the pairs are distance at most 4. So for that, an important fact is that whenever you take any 4 vectors, you know that there is an index where they take all value 1. So this way you can define, for instance, if you want to check that from ABC to DCB, all the pairs have distance at most 4. You define those 3 indices, and this path of length 4 between any vertex of ABC to any vertex of DCB exists. So let's check just the beginning. So for already this vertex to exist, it means that A should take value 1 at ijk, which is the case. You find A here, here, and there, and B at least 2, which is the case with I and J. And finally, for this edge to exist, there should be an index where both B and C takes value 1, and this is the case with index I. So you can check well, the rest of the path, but also the other cases in a similar fashion. Now, if there is an orthogonal quadruple ABCD, then the distance between ABC in ABC and DCB in DCB is 7. So there is no path of length at most 6 between those 2 vertices. You can check that it's the case if you use vertex U or V. Now we ignore U and V and we consider either we take a skew edge or not. So if we don't take a skew edge in our path, there will be in the path 2 vertices ABijk and DCijk, and their existence implies that there is an index where A, B, C, and D takes value 1. If, on the other hand, you take at least one skew edge, then your first two edges or last two edges will have this form. And again, the existence of this vertex and of that edge, you can see that it implies that there is an index among I, J, K where A, B, C, D are 1, again a contradiction. So that's all for me. I thank you for your attention. I want to report some further developments. So independently, Lee and Dalio-Ford and Wien showed this series of lower bounds in the directed unweighted case, tightly complemented by Lee by an impossibility to show SETH lower bounds in that region here. And recently I showed the same lower bound, but now even without edge orientations. So this is what is currently known for undirected unweighted diameter. And again, thank you a lot for your attention.